Welcome back to the Deep Dive. Today, we're tackling something absolutely crucial, something that's running silently, hopefully, in your car right now. Automotive functional safety. And specifically, we're going to unpack the software side of things. Our mission really is to pull out the key insights from this major international standard, ISO 26262. We're zeroing in on part 6, which is all about product development at the software level.
Yeah, that's the core of it.
So if you've ever wondered, how all that complex code in your vehicle is designed to be fundamentally safe, well, this deep dive should shed some light on the really meticulous process behind it all.
And what's fascinating here is ISO 26262, it's not just some document collecting dust. It's really the bedrock for safety in all the electrical and electronic systems in vehicles today.
Right.
And part 6, that's like the brain of the safety operation and lays down the law, basically, for how you build functional safety into the software itself.
So it's not just about code that works, but code that works safely.
Exactly. It's about preventing hazards, mitigating harm if something does go wrong. And it's crucial to note, like you said, this part isn't about making the car perform better in a nominal sense, faster acceleration or whatever.
No.
It's purely focused on the safety aspects, preventing accidents, reducing injury severity. And it applies pretty broadly new systems, integrating older stuff, standard production cars.
So it's baked in from the start, not bolted on at the end. It's really about designing safety in. And you mentioned a key concept there, the V model.
The V model.
Here's where it gets really interesting because it sounds maybe a bit technical, but it's actually a pretty intuitive idea, right? Think of it like a roadmap.
Yeah, a visual roadmap.
For every step you take designing something on one side of the V, there's a mirror step on the other side. It's all about proving it works safely.
Exactly. Verification.
It creates this closed loop traceability, I think is the term, making sure safety needs flow down and the proof flows back up.
That's it precisely. Think of that V. Down the left side, we're defining and designing. It actually kicks off with the technical safety concept, which technically comes from part 4 of the standard. That's the big picture. What needs to be safe system-wise.
Okay.
Then that feeds into the specification of software safety requirements, the SSRs. This is where we get specific about what the software must do for safety.
Translating the big ideas into code tasks.
Right. Then comes software architectural design. How are we going to structure the software? What are the main components? It's like drawing the blueprints for the software house.
Okay.
And finally, at the bottom of the V, you have software unit design and implementation. This is where the actual coding happens for the smallest testable bits, the units. Think of them as the individual bricks in that house.
Right, the bricks. And then once you've laid the bricks and built the structure, you start climbing up the other side of the V.
Exactly. Time to prove it all works.
This is the verification side, putting it all to the test.
Yeah, precisely. Rigorous testing. First up, software unit verification. Testing each individual brick, basically, making sure it does exactly what it's supposed to and safely.
Okay.
Then, software integration and verification. We start putting the bricks together, building walls, sections, and checking they work correctly together.
Checking the interfaces, how they talk to each other.
Absolutely. Then, testing of embedded software. Now we take the whole software package and run it on the actual target hardware, the ECU it'll live in.
Getting closer to the real thing.
Yep. And the final confirmation, mirroring the start, is system and item integration and testing, again from part 4, ensuring the whole system, hardware, and software together in the vehicle context meets the overall safety goals.
Wow.
And throughout this whole journey, you're generating evidence, documents, code, test results. These are the work products. They prove you followed the process. And the really crucial piece, tying it all together, that traceability matrix.
Ah, yes, the thread connecting everything.
It's the golden thread. It links every requirement to its design, to its code, to its tests, to the results. It's how you demonstrate irrefutably that every single safety aspect was addressed and verified. No gaps.
That sounds incredibly thorough, almost dauntingly so. So let's dive into those requirements a bit. What makes a software safety requirement, an SSR, different? What's in it?
Right. The SSRS, the specification document, it's foundational. The key thing, the real insight, is that every single SSR isn't just floating there. It has a direct lineage back to a higher level safety goal defined in the system's safety concept.
Like a safety family tree.
Exactly. Each one needs a unique ID, a clear description of what it needs to do, and critically, a rationale. Why is this necessary for safety? You can't just say, do this. You have to justify it from a safety perspective.
Right.
And then it's ASIL level. Automotive Safety Integrity level, A, B, C, or D.
That's the criticality rating, right? D being the highest.
Yeah, correct. D is for systems where failure could lead to severe or fatal injuries. A is for things where failure is more of a nuisance or minor risk. This ASIL dictates the level of rigor needed for everything that follows design, testing, verification.
So the standard tells you how careful you need to be for each specific function.
Pretty much. The SSR also has to state how it will be verified, what test method, and the acceptance criteria, how do we know it passed, plus dependencies on other requirements, and often the safety mechanisms involved.
It really is like a mini contract for each safety function. Can you give us a feel for the difference, like an ASIL A versus an ASIL D requirement?
Sure. Let's think. For ASIL A, maybe something related to driver information, but not immediately critical, like the software shall display the service due reminder when the mileage threshold is reached. If it fails, it's annoying, maybe affects maintenance, but unlikely to cause an accident directly.
Right. Inconvenient, but not dangerous.
Now, jump to ASIL C. We're talking potentially serious injury, maybe something like the software shall detect a sustained unintended acceleration request above threshold X for Y milliseconds in limit engine torque. That's preventing a runaway situation.
Oh, okay. Much higher stakes.
Definitely. And then ASIL D, highest level. Think critical braking or steering functions. An example might be, the software shall detect the failure of the primary steering angle sensor within 10 milliseconds and activate the redundant sensor pathway to maintain steering assist. The speed, the consequence, it's life critical.
Wow, the timing requirements alone show the difference.
Absolutely. And beyond these specific function requirements, the SSRS covers things like fault detection and handling what happens when things go wrong. How does it transition to a safe state? How robust is it against garbage inputs? It's designing for resilience.
Okay, so once you have these super detailed ASIL-rated requirements, how do you design the software structure of the architecture to actually meet them safely? That's the software architectural design phase.
That's the next big puzzle. The goal here is to take those SSRs and map them onto a logical software structure. But it's not just about functionality. The architecture itself has to support safety. It needs to be verifiable, manageable, and critically, it must ensure freedom from interference, or FFI.
FFI, freedom from interference. Tell me more about that.
Okay, imagine you have your supercritical ASIL-D braking control software running on the same processor as, say, your ASIL, a climate control logic. FFI means you have to guarantee architecturally that a bug or crash in the climate control code cannot negatively impact the braking code.
Ah, building walls between them.
Exactly. Invisible but robust walls. The main output here is the software architecture design description, the SADD. It's the blueprint showing these components, their interfaces, and how they ensure safety.
So what are the key principles for building this safe architecture?
Big ones include modularity and encapsulation. Break the software into smaller, manageable chunks or modules, each with a specific job and well-defined interfaces. Keep their internal workings hidden and encapsulated. This limits the ripple effect of changes or errors.
Like building with well-defined Lego bricks again.
Kinda, yeah. And related to FFI is independence of safety-related functions. You need to ensure that functions with different ASIL levels or even different safety functions at the same ASIL level are sufficiently independent. This can be temporal independence, guaranteeing each critical task gets its required slice of CPU time, using things like scheduling priorities and watchdogs.
So they don't starve each other for processing time.
Right. And spatial independence, giving critical functions their own protected memory regions so one can't accidentally overbeat the memory of another. Think memory partitioning units, stack overflow protection.
Got it. Temporal and spatial walls.
And also designing to avoid single points of failure architecturally. You don't want one central component whose failure could bring down multiple safety features. Maybe using diverse monitoring paths or ensuring the system can degrade gracefully rather than failing completely.
Designing for resilience again. Makes sense. How does this translate down to the actual code level? The software unit design and implementation.
Right, down to the nitty-gritty. A software unit is the smallest piece you can realistically test in isolation. Each unit needs its own mini specification, the unit design description. It details its job, its inputs, outputs, error handling, resource needs like execution time and memory, and critically, its ASIL level and traceability back up to the requirements it implements.
So even the smallest piece has its safety contract.
Exactly. And a huge part of this phase is adhering strictly to coding guidelines. You don't just write code however you feel like. Standards like MISRA-C or CERT-C are often mandated, especially for higher ASILs.
Ah, the MESRC. Heard of that. What kind of rules are we talking about?
Think things like Use strong typing, avoid ambiguous language features, use fixed width integer types so you know exactly how big numbers are, no implicit type conversions that might lose data, ensure loops always terminate, use defensive default values and switches, be incredibly careful with pointers. It's all about writing code that is unambiguous, predictable, and robust.
So it forces a very disciplined style of coding to eliminate potential bugs up front.
Precisely. It reduces the risk of introducing subtle errors that are hard to find in testing, and these practices become more stringent as the ASIL level increases.
Yeah, so.
Well, for ASIL C and D, techniques like defensive programming become highly recommended, HR, in the standard, whereas they might just be recommended R for A or B.
And the defensive programming is?
It's like coding with paranoia. Assume inputs might be invalid, check them rigorously, use saturation arithmetic to prevent overflows, put time limits on operations, have fail-safe default behaviors, use assertions to check assumptions, handle errors, gracefully detect, isolate, mitigate, log, maybe try to recover. It's building self-protection into the code. Same for memory management. For high ASILs, you strongly prefer static allocation reserve memory up front. Avoid dynamic memory allocation, like malloc and C, within safety-critical units because it can be unpredictable and lead to fragmentation or failures. Strict bounds checking on arrays is essential.
Makes sense. Keep it predictable.
And heavy use of static analysis tools. These tools scan the source code before it's even compiled or run. They act like automated expert reviewers, finding potential issues like using variables before they're initialized, dead code that's never reached, potential null pointer accesses, complex code that's hard to test. It's like getting an X-ray of your code to spot hidden problems.
Okay, so the code is written super carefully, following strict rules checked by tools. Now the big question, how do you prove it all works safely? We're back on the right side of the V verification and validation.
Exactly. This is where you generate the objective evidence. It starts with software unit verification. We need to show each little unit does its job correctly according to its design description and handles potential faults.
How do you test such small pieces?
Several ways. We already mentioned static analysis. That's a key verification technique, not just a development aid. You generate reports showing rule violations or lack thereof. Then there are code reviews and walkthroughs.
Human eyes on the code?
Yep. Peer reviews, formal inspections, using checklists, logging findings systematically, combining automated analysis with human expertise is really powerful for catching different kinds of issues.
Okay. And actual testing, running the code.
That's unit testing. Here, you isolate the unit using test harnesses, drivers, and stubs, basically. Bits of code that pretend to be the unit's environment. You use white box techniques where you design tests based on the code's internal structure, making sure you execute specific paths, test boundary conditions.
Looking inside the box.
And black box techniques, where you design tests based purely on the unit's requirements. What should it output for given inputs, regardless of how it's coded internally? Equivalence partitioning, state transition testing are common methods here.
Makes sense. Testing from both perspectives. What about coverage? You mentioned that earlier.
Crucial. Coverage requirements measure how thoroughly your tests exercise the code. It's not enough to just run some tests. You need proof they covered the logic adequately. Basic is statement coverage, did every line execute. Better is branch decision coverage, did every if statement go both true and false.
And for the really critical stuff.
For ASIL D, the standard typically demands MCDC coverage, modified condition decision coverage. This is quite complex, but basically for every condition within a decision, like if A and B, you need tests that show that changing just that one condition, A or B, actually changes the outcome of the whole decision while keeping other conditions fixed. Yeah. It's incredibly rigorous for finding subtle logic errors.
Wow, that sounds intense.
It is. And finally, for units, there's fault injection and robustness testing. Here, you deliberately mess things up.
Break it on purpose.
Kinda. You simulate faults, bad sensor inputs, memory errors, communication glitches, and verify that the unit detects the fault and behaves according to its specified failure mode, ideally entering a safe state.
Okay, so unit testing is incredibly detailed. Then you integrate them. Software integration and testing.
Right. You've verified the bricks, now you build the walls and check the structure. The goals here are to verify that the units work together correctly, that the interfaces match up, and importantly, that the overall software architecture itself fulfills the safety requirements, especially things like freedom from interference.
How do you test the architecture?
Through integration tests. These focus on the interactions between units or larger components. You might run stress tests specifically designed to try and force interference between components of different ASIL levels. You verify communication protocols, data sharing mechanisms, timing interactions under integrated conditions.
And this is often where hardware in the loop, ATOIL testing, comes in, right?
Very often, yes. HIL is vital for automotive. It lets you test the actual ECU, the hardware, with the integrated software running on it in a simulated vehicle environment.
So fake engine, fake brakes, but real ECU.
Exactly. You have powerful computers running real-time models of the vehicle dynamics, sensors, actuators. The ECU is connected via real electrical interfaces. This allows you to test complete scenarios, inject faults, run regression tests automatically, all in a safe, repeatable lab environment. You can simulate things that are too dangerous or difficult to test on a real track, like sensor failures at high speed.
That sounds like an incredibly powerful tool for realistic testing.
It's indispensable for validating complex control systems safely and thoroughly. You also do detailed interface testing here, checking electrical signal quality, functional contracts across interfaces, timing, protocol robustness, even diagnostic interfaces.
Okay, so units verified, integration verified, architecture check, HIL testing done. What's the final step in software verification? Tying it all back.
That's the overall software verification against safety requirements. This is where you formally demonstrate that the entire software product as a whole fulfills all its specified software safety requirements, SSRs, and doesn't violate any higher level technical safety requirements, TSRs. It's about closing that V-model loop definitively for software.
And how is that documented?
Often in a software verification plan, SVP, upfront, outlining the strategy, and then in a final software verification report. The core principle is requirements-based testing. Every single SSR must be traced to one or more test cases that prove its implementation is correct.
And traceability is king again.
Absolutely paramount. You need that requirements traceability matrix, RTM, showing the links. Safety goal, guidance, TSR, SSR, software architecture, software unit, test case, test result. It has to be bidirectional. Tools are essential here to manage this complexity.
Makes sense. What happens if tests fail? You find problems. Anomalies.
It happens, of course. An anomaly is any unexpected behavior. The process is rigorous. Detect it, record it meticulously, analyze it, triage, assess its safety impact. This is critical. Is it just a functional bug or does it affect safety?
Yeah.
Then decide, fix it, find a way to mitigate the risk, maybe add a monitoring function, or very rarely request a deviation or waiver. A waiver means you accept the non-compliance, but only with solid justification, risk analysis showing it's acceptable, potentially compensatory measures, and formal approval.
So you can't just ignore problems.
Absolutely not, especially safety-relevant ones. Root cause analysis, RCA, is key to understand why the anomaly occurred and prevent recurrence. Everything, the anomaly, the analysis, the fix, the retesting, any waivers must be documented in the safety case, which is the overall argument that the system is acceptably safe.
Wow. It's a very disciplined process for handling issues. Now, this all sounds quite document-heavy and process-intensive. What about newer ways of working? You hear a lot about model-based development, MBDV. How does that fit in?
MBDV is a really powerful approach that fits very well within the ISO 26262 framework. The core idea is using models, often graphable, like Simulink diagrams, to represent the software's functions and behavior.
Instead of writing code directly, you draw diagrams.
Sort of. You model the logic, the control algorithms. The huge benefit is that these models can be simulated very early in the process. You can test your design before writing much, if any, code.
Catching problems much earlier.
Exactly. Models can be less ambiguous than text requirements. You can often automatically generate test cases from the models and even automatically generate the actual production code for the ECU.
Auto-coding. That sounds efficient, but maybe risky.
It can be both. The benefits are consistency. The code directly matches the verified model and speed. The risks involve potential errors in the model itself or issues with the code generation tools. That's why the standard has requirements for validating the models and qualifying the tools used, especially for higher ASILs.
So MBDV doesn't replace the V model, but integrates with it.
Precisely. You can use models for specifying requirements, designing the architecture, designing units, generating code, and generating tests. It applies across the whole V. The key, as always, is maintaining rigorous validation and that crucial bidirectional traceability, linking the requirements to the model elements, to the generated code, and to the test results.
So it modernizes the how, but the fundamental safety principles and the need for proof remain the same.
Exactly. It can make achieving compliance more efficient and potentially less error-prone if done right.
Okay, so wrapping this up, what's the big takeaway for you, our listener? We've really journeyed through the depths of ISO 26262 Part 6, and it's clear this standard provides an incredibly structured, detailed, almost meticulous roadmap for building safe automotive software. It's not an accident, it's safety by design.
Right.
From those initial precise safety requirements, through careful architecture and unit design with strict rules, all the way to exhaustive testing and verification, often using advanced methods like HIL and MBDV. Hopefully, you now have a much clearer picture of the hidden engineering that goes into making sure the software in your car is working constantly to keep you safe.
And maybe this raises an important question to think about. We see how detailed this standard is, designed to manage risk and build trust in these complex systems. But automotive software is evolving incredibly fast, right?
Totally. ADS, autonomous driving.
Exactly. Advanced driver assistance, more AI, machine learning components finding their way into safety functions. So the provocative thought might be, how will standards like ISO 26262, based on these deterministic principles, need to adapt or evolve to ensure safety in systems that are inherently more dynamic, perhaps even non-deterministic, like AI-driven perception or decision-making? That's the next big challenge.
That is definitely something to mull over. How do you apply this level of rigor to something that learns and changes? A fascinating question for the future. Well, that was quite the deep dive into ISO 26262 Part 6. A huge thank you for joining us on this exploration of automotive software safety. We hope it's given you plenty to think about until our next deep dive.